All right, it's time. So today we're going to be doing back propagation. We're doing the whole Monday thing. I'm trying it out again. I think this one's going to be a little bit more helpful for everyone. We'll see. And we're going to be doing back propagation. There it goes. All right. So first things first. Let's talk about homework. let's talk about homework too. So, just so that everyone can be on the same page as me, how many people have finished homework 2? There you go. If you thought it was pretty hard, you're not alone. So this is hard, and I'll admit probably too hard, and I can see that. I will tell you that this is going to be the hardest assignment in the entire semester, maybe besides the final project. That's on purpose. We need to front load all of this stuff now so that you can get the good stuff later. We can cover more content this way. Think of it as eating your veggies to get your dessert. We're doing cool stuff later. This stuff is very important, though, that you guys actually learn how to do. That's sort of the entire point of this class. So this homework is here to stay. But let's talk about it. So, for one, there are a couple bugs, and I just want to make sure that everyone's on the same page with these. I posted on Piazza, but I want to make sure that everyone knows. One, I wrote sigmoid as this. In class, too. Sigmoid is actually this, where we have e raised to the negative x, not just x. I did it correctly in the solutions to the homework, but not in class or on the written part. So just so you know, messed that up. Secondly, on lines 29 and 32 of the homework, when I was importing the data, I put this line instead of that line. The difference here is between taking just the third from the last element and taking the last 3 elements from the array. This meant that the data that you were comparing to, the prediction or the labels, were only 1 long when they should have been 3 long. That sucks because some people kept getting dimension errors, which they would assume is their fault, but instead it was mine. Great. So that's 2 characters that I missed, and it caused a lot of headaches for some people. And also, the autograder wasn't working. It now is. There's, again, a single character was wrong. So that's 3 characters and a lot of trouble. Anyway, so with that, oh, one more thing actually I didn't put on here, but also, in the equation for the model, I put bias outside of sigmoid. You could do your model like that, but for the sake of this homework, we're doing it inside the sigmoid. Another small mistake. Anyway, it's a new class. It's a new class. I can make mistakes, right? I'll try to earn the goodwill back. Don't worry. All right. So, what am I going to do about it? Well, there's a lot of different ways I can handle this. The fact that this homework is too hard. So, first up, I am going to be doing a coding walkthrough of this homework like I did last Monday. This one is going to, like the last one, go through everything you need to know to do the homework. We're going to do the math, we're going to do the coding, and we're going to, inside this lecture will be everything you need to do the homework. That said, this homework is a little bit more difficult than the last homework, and I expect that won't be enough for some people immediately, considering it's due tomorrow. So, I'm also going to let you all vote on how we're going to handle this. All right? So I want you to all have to deal with this situation the way I do. It's a hard question what to do in this situation. I'm gonna seek your input. Now, to be clear, this is a dictatorship, and I will make the final call. But I'd like to hear what you guys think. And if everyone feels the same way, I think it's pretty likely that you guys are going to do something that's going to be a good idea. You guys will make a decision that's a good idea. In general, students will make decisions that will be easy for them in the short term, but don't really worry about the long term. So I'm going to take that into consideration. Sometimes students do make bad calls about what to do content-wise. 3, I'm going to try to do these Monday recaps a little bit more official. I think they've been helpful for people from what I've heard, and the fact that this homework was so difficult for everyone, I think means that it is necessary to a degree. I'm going to try it out still. I mean, if I decide to change it, remember, it's a dictatorship. I can do that. But I will try to make it regular so that there is, if you're having trouble with coding, there should be a time for you to be able to catch up. And for everyone, for harder homeworks. And 4, I'm going to do a couple more polls. I know that that's maybe a bit much, but again, it's my first time teaching a real class, and I want to, figure shit out so that you guys don't have to entirely be guinea pigs. Just early semester you can, and then I'll figure my stuff out by the end. Anyway, so we're going to start with a Kahoot. See, I told you I'd earn the goodwill back, right? All right, so this is the link right here. If you want, I did post a lecture on Piazza, so you can go look at it. There's not much on this lecture, though, because most of it is just a coding notebook. All right, so let's do it. It's on the slides. Yeah. All right, there you go. I just realized we don't get the music because the sound doesn't come through. That's sad. Wait, actually, is it? Yeah. What did I do different? Whatever. We got the music now. Oh. By the way, I really appreciate everyone's restraint in not pointing out the fact that my Windows is not activated. All right, I'm going to give it 10 more seconds. If you're trying to think of a name, just put something random down. I guess if you can't join, just work with a partner, too. All right. All right, let's do it. So, first up, we're going to do the polls. So, first, do you wish there were more office hours? Either yes, with either a TA or me. Yes, but just with me, like particularly my office hours. Or just with the TA, or no, you don't want any more office hours. All right. I'm still deciding whether to do more office hours if you didn't pick up on that. All right. Yep. All right, cool. All right. Well, looks good. Looks good. All right. Nice. Thank you. We're doing a couple polls first, and then we'll get to the ML stuff. Don't worry. So what's your main problem with homework 2? Is it using Python, including the code format that I set up, the instructions, like the written instructions, the math, or just the length? But what? Yeah, I mean that's fair enough. That's fair enough. All of the above? Oh man. All right, all right. Someone's really weighing this out. I don't know, the math was really bad, but so were the instructions. That's okay, it's okay. Again, I am self-aware. I do realize that this homework didn't go over that well for you guys. All right. Well, someone's still waiting on it. All right, that's fine. Let's see. The instructions and the length. That makes sense. All right. Okay. Cool. Thanks. All right. What do you think should be done about the difficulty of homework 2? Should we extend the due date, do more office hours tomorrow before the deadline? Should we weigh this homework lower, but give the same amount of deadline? Or should we do nothing? Should I do nothing, I guess? All right, I want to see if you guys can be unanimous on this.
Is there an option for making it
Yeah, go for it. So, select green, I'll take it that way. Yeah. And that one person is still thinking really hard about it, huh? All right. Okay. All right. So I will say the downside to moving the due date back is, one, that you might come to expect it in the future in the back of your mind and not get them done by the due date. This, by the way, I think will be the only homework that this will happen for. All the other homeworks should be easier, but I also missed this one, so who knows. And secondly, we will be able to cover less content. In particular, I scheduled a large block of time at the end for us to work on final projects and go through some more modern machine learning stuff. So we're probably, if I extend the deadline, are going to be changing that a bit. Question?
What if we just had the written portion due every week and then have the coding portion slightly longer for each assignment?
Yeah, so that was a consideration, actually. So this is a whole, I'm going to have a rant about being a teacher again. I went back and forth a lot about how to do these homeworks, and this is what I landed on, right? And that was definitely an option. The main concern with doing it that way, where you have the written portion due at a different time than the coding portion, is that either people will just do the written portion and then forget about it and go do the coding portion, where they are extremely related. I think you'll all acknowledge. And also, a lot of the written portion has to be based off of the code. So no matter what, I think we still end up with a similar problem. Yeah?
What if you didn't want to do less material? What if we just as far as extensions goes, we just had a few more days rather than a whole week?
That's fair enough. I think. So there's a whole other thing to think about is consistency makes it a lot easier for a lot of students. If they're always due on the same time and the same day of the week, then people are able to put into their schedule and build a schedule. It makes it way easier to actually get the homework done. So I like to always have the same due date no matter what. And also giving a couple days then throws off when do we start the next homework and et cetera. I don't want to wiggle the schedule too much. Yeah. We were having a whole discussion about this. I didn't expect that. Oh yeah.
What did you say the downside was of the 1 week extension?
We can cover less content is the main thing, and it basically is slowing down the class a little bit and saying this is too fast. Let's chill out a bit. Yeah. Yeah.
Your extension policy is 5 days. So
yes.
Maybe you can just add 3 days and.
Yeah. I think. So I've kind of already made up my mind. Oh yeah, another one. Yeah.
Just maybe instead of extending the deadline, instead of doing the homework, noticing a recap and everything on the Monday break, once you do it on the Thursday before the weekend, so we have more time.
Yeah. So the Wednesday before, presumably, because during this class, yeah. No, that is a good idea. I think the timings for it just didn't line up with how I planned the classes. I mean, I'll give it some consideration for the future, but what I'm going to do in the immediate, this is the final decision on this. This homework will be due next week. You can, I did not, okay. Yes, applaud me. See? Turning bad assignment writing into applause. That's a teacher move. All right. Anyway, okay, so that's handled. I hope that's a little bit less stress for all of you. We are still going to be covering all of this stuff today, still do it. And I think you all now have realized that it's difficult and you should take some time with it. Yeah.
I have a suggestion.
Yeah.
Again, to combat the whole, I know you mentioned you would be able to cover some of the new stuff or fun
Yep.
stuff. What if
Yeah, no, it's not so much that we can't cover as much content in lecture. It's that we can't cover as much content in homework and in projects. That's the issue. Because, for all the lectures you get up here of me saying, this is how you do back propagation, and this is how you do whatever, as you've now shown, that's not the same as knowing how to code it. That's not the same as knowing how to do it. So we need you to do homeworks. That's why homeworks exist in this context. I'm not a big believer in homeworks that are like frivolous, just like copy and paste what you know from lectures. I want them to be, once you finish it, you're like, I know how to do machine learning now, and we need that. Yeah.
If the homework is the deadline is like 7 days a week,
Mm-hmm.
so that would be fine, I think. So Thursday release and Thursday.
Yeah. That's not a bad suggestion. So my whole concern, I said this before, was that I was worried about people skipping lecture to work on the homework. And I also don't want the homeworks to overlap. So saying Thursday means that if we release them every week on Wednesday, then there is an overlap, and that just stresses the hell out of people, I've found. I think that's a little bit what the like free late days are for, is that you can extend them. And there's only 4 homeworks, I think, that you will actually care about using late days. Everything else is going to be final project stuff. So, use them. I think I can't make it Thursday because of the overlap, just because I don't think that's like good for people. And I want to have it be an even day, like week interval, so that it's always on the same day of the week. I'll consider it. If you have suggestions, feel free to email me. But really the whole point of this is homework is due next week, next Tuesday. And we're going to be going over it again today. So hopefully even after this lecture, you'll feel like maybe the deadline's actually not that bad, because now you feel like you know it. Hopefully. We'll see. All right. Now we do actual quiz stuff. Now we're actually getting to it. The model below, 2 matrix multiplications, can exactly solve problems blank compared to a single perceptron. Either faster than a single perceptron, more difficult problems than a perceptron, only equally as hard problems as a perceptron, or problems without a nonlinearity compared to a perceptron. A big change of pace all of a sudden, huh? By the way, for this, if you want to work with a partner, I'm cool with that. If you want to work with the person next to you, I think it's actually perfectly fine. Let's take away a little bit of the glory of winning, though. All right. Talked about a whole bunch of stuff. What were they? Nice, nice. All right, it looks like people know why to hate sigmoid. So, yes, if we have a very big input going into sigmoid, if we look at it, we see if we have a high magnitude input, if it's high magnitude positive or negative, we see that it flattens out, which means that its derivative goes towards 0. This is an issue because when we go to take the derivative of it, it is close to 0, which ends up causing our gradient to be close to 0, which means that we don't learn very quickly. We don't like that. Secondly, it doesn't output any negative numbers. This is also true, as you saw in it. Negative numbers do help give, like they're a different class of numbers when we're doing some comparisons. If you're subtracting a number, that's very different than adding a number. Yeah. So that is not an issue with it. The reason being, what we're going to talk about today. We can just memorize what the output is and then use that to resolve it. We don't need to ever recalculate it. Yes?
Can you repeat your point about the negative numbers again?
Yeah. So we like our nonlinearities to have negative numbers. We like our models to have negative numbers because it allows us to have certain inputs that affect things negatively. For example, if you have some input to your thing, like hours of sleep and all of that, compared to if we have like amount of drugs taken the day before the final, you might want that to negatively influence what your final score is, or you might want that. If we take away the ability for negative numbers to exist, then the best we can do is just setting it to 0, if we think that's a correlation. Anyway, and then the last one, its output is always smaller than its input, is not true, actually. If we look at x equals 0, it gives 0.5, which is not less than 0. All right, cool. Next up. Steve Jobs, sorry, I'm very sorry. All right. True or false? In the model below, to calculate the derivative of y with respect to w0, we must first calculate the derivative of y with respect to w1 and the derivative of y with respect to w2. What do we need to calculate the derivative of y with respect to W0. It's a nuanced point about how we do gradient descent. The answer is false. If we look at this, sorry if this is demotivating for everyone. They are still like a little bit tricky questions, so don't worry too much about that. But if we look at it, so say we want to calculate the derivative from y to W0. How do we use our computation graph to calculate the derivative of something? Yeah.
Solve the derivative in the path of the variable you're trying to solve for?
Find the derivative along the path to that variable. Let's take a look at it. That is true. So if we're going from y to W0, we'll calculate the derivative from y to 0,2 to O2, then from O2 to O1, and then O1 to W0. Along that chain, we never come across any of the other parameters. It's a common misconception, because of the way that neural networks are usually talked about, that we need to calculate the derivative of weights in the later layers before the previous layers. We happen to, but it's not a requirement. We'll look at that again today. And last question, I think. Steve Jobs, still up there. Not Cooper falling behind. To calculate the gradient of loss, we must first calculate loss itself. Again, a bit of a nuanced point about how we calculate gradients. (50-50) nearly. It is false. So let's think about mean squared error. Right? Mean squared error, let's just say we just want to look at something that does mean squared error. We just want the derivative of mean squared error given some input. So mean squared error is those things subtracted, so it's y minus y hat squared, or the other way around, it's fine. And if we take the derivative of that, we find that it is 2 times that inside. So 2 times y hat minus y. Now, we can just take that derivative, which is just those differences, and we never calculate a square. We never actually calculate the mean squared error. We happen to calculate the loss because we'd like to report it, because we want to know how well our model's learning by looking at the loss. But we never actually need to calculate the loss to calculate the derivative of loss. Does that make sense? Cool, cool. It's, again, another little bit of a nuanced point, but I think all of these nuanced points together make it a lot easier to understand what's going on in the whole. All right, last question. Training on some data may cause our model to perform worse on data it wasn't trained on. Just a fact. How can we fix this issue? 1, train on all of the data, as much data as we have. 2, train it on less data. 3, make the model smaller, i.e. having fewer parameters. Or 4, manually change the hyperparameters until it does well on the new data. I talked about this a little bit last class. Oh man. All right. Hey, we got a majority. So yeah. The way that we'd go about doing this is we would look at the, so we would train first on, say that we have the purple and the blue, which are the different colors we had in our example. Let's say we want to look at the purple, and we want to have it fit all of the data, but we only train on the purple. If we train it a lot on the purple, we might end up right in between here. But if you imagine if we had, say, a lower learning rate, and we didn't learn as much, we might end up with a line that hasn't fully reached here. Or maybe we have a higher learning rate and it jumps across and changes its trajectory and now it's facing down. So these are not optimal solutions for our training data, but if we look at our testing data, it actually ends up being better. So the convention of how we deal with this problem is that we look at how to tune the hyperparameters. So we're going to look at all the hyperparameters, and the metric that we compare them to is how well it does on the other data that it wasn't trained on. So it's called hyperparameter tuning. It's a pretty big concept. We're going to talk about it later. It's not a big issue for you guys now, but it's important for you to have that in the back of your minds. I'm going to keep repeating this until when we talk about it, it'll all make a lot of sense. All right, cool. Let's see how that turned out. Amaya, congratulations. Boss baby god. Is it Steve? Is it Steve? It's Steve. Congratulations. Nice. All right. Cool. All right, so that was still a little bit hard and all that. But let's now take a little bit of time, the rest of class. We're just going to look at how we actually code backpropagation, how we go about doing this homework, and we're gonna do all of the math that we can in the rest of the time. All right, not just the math, the coding. So here's a notebook. If you want to follow along, it is linked on Piazza. Go to lecture slides and you can find it. But let's look at this. So I'm gonna make it bigger. All right. So again, like always, we're going to do our imports and stuff. This is just how you do it in Notebook. So let's just import it. Woohoo. Run anyways. All right. So there we go. We're also importing this new library, TQDM. We may use it later, we might not. This is how you get a loading bar, just in case you're curious why there's a new thing there. Resources. Yeah, all the lecture slides are on Piazza and under resources. I also usually post them on Moodle, but I haven't posted this one because class had to start. All right, so we got this now. I'm going to load in the data set. I'm just doing it like this because why not? And this data set that I'm using right here is exactly the same data set you have in the homework. So we're also going to talk about the data set a little bit. I know I didn't do that much in class, but we're going to look at it and we're going to see what the data set is. All right? So this is just setting the train data. So this is the train inputs, train outputs to being the first 800 inputs. That's just what we did on the homework also. So what is the data? So the data has 5 input features. We have sex, race, parental level of education, free or reduced cost lunch, that's if they got a free or reduced cost lunch, and completion of test prep material. For each of these, I used a one-hot encoding. So one-hot encoding, it's not particularly important, but it is very useful if you want to do any of these things. It's when we encode each of a number of possibilities. For example, for sex here, we had male and female. So I would encode male as 0, 1, and female as 1, 0. This is a little bit better for us than just doing 1 and 0 as a single bit, because now we're allowing both of them to have positive inputs. So you can imagine if we have just an input of 0, our model will most likely output 0. This is allowing us to have negative things, which is another reason why we like having negative numbers. So that means that we have a dimension of 17. This totals up to 17 bits. So they're all 1s and 0s. All of our inputs are 1s and 0s. So it's actually a fairly simple data set. We can print out here and we can see it is exactly just 1s and 0s. And there are 800 examples. That is the number of rows. And each one is 17 long, which is the number of columns. All right? So the output features are going to be 3 values. Their score in math, their score in reading, and their score in writing. They're all going to be float values. Yes?
So for the input, would it be just different ways of organizing those different groups? Like, it would be like a male who does this, who does this?
Yes, so all of them are particularly identified by which of the bits are 1 or 0. So yeah. All right, and then the output are 3 floats. If we just print it out, I already did, you can see that these are scores. So there are 800 of them, and they're all 3 long. This is the thing I messed up before where I only had a single value in them. But here you can see I changed it so that it has the correct thing here. All right, so this right here is just going to be a, this is just a helper method. It's not for any of the, for the machine learning. All it is a function that will translate what the input was into an actual data point. It will actually describe it. So it converts all those bits back into readable features. So if we look at student 50, they are a male of race A. They obscure the races for the sake of the data set. They had some college in their parents. They do not get free or reduced lunch, and they did not do test prep. And they got a math score of 53, reading of 55, and a writing of 48. So that's an example of a data point. If we just want to feed in a random one, so let's say that we have the 20th. Let's do this. 20th, they're now a male of race B with high school education, no free lunch, and that. So you can see that each one of these data points have their own unique identifiers. All right, so let's ask ourselves the question of which features will tell us whether the student is going to do well or not. So what matters? Does test prep matter? Does their race matter? Does their parents' high school or their parents' education level matter? So what of these things are actually seen in the data? So first, we need to initialize our model. So let's start with a very simple model. Let's say that our very simple model is going to be a one-layer perceptron. All right, so we're going to start with one layer, and then we're going to generalize as we go. So let's say that we want our weights are just going to be np.random.randn times whatever dimension we want, which is in this case 17. We can have it be, so layers is going to give us all the layers we want. So in the very simple case of one layer, it will be 17, then 3. So we can just say something like this if we'd like to. So we have layers 0, which is going to be 17, it's the input, and then layers 1, which is going to be the next one. And we'll see that this does generalize very nicely for us. And then we're just going to set the bias. And what should be the size of the bias? Anyone want to tell me? Size of layers 1. This is because this function right here, so this weight matrix, we're going to multiply it. And remember that the dot product works something like this. If we have something of size A by B, so say we have something of size A by B, and it's being dot producted by something of size B by C, this will give us something of size A by C. So in the case of our computation, we have this A, which is the number of data that we're importing. It will never actually affect anything down the line, and we can essentially treat it like it's 1. I know that's a sort of a weird idea for us, but essentially what we're doing is we're doing the same operation to every single data point. That's like how this works out. So we can sort of just ignore it, and what we care about is having the bias be this size. So we're applying the bias after this matrix multiplication, so then if we add something of size C, this will remain as a size A by C, and we'll apply that C addition to every single row. So we want to treat every student exactly the same, right? We don't want to treat every single student as having their own individual bias, because then that will just overfit us to certain examples, and that won't be good. So instead, we are applying it to every one of these students. All right? So just comment that out. Anyway, so that means that we care about layers 1. All right, so now we have to add them to the dictionary. So I'm having you guys use a dictionary, which is an unusual data structure for some people, but it is a very useful one for the sake of this, because it's very natural for us to have keys or indexes that are going to be strings. This is the main reason we're doing this. The other reason is that it's faster to query from a dictionary than from anything else. This is a very natural way for us to actually code machine learning properly, but it is a little bit difficult if you haven't seen them before. So what we would do if we want to set certain parameters of this is we give it some key. It's exactly the same as listing in terms of how you use it. We just give it some index. It just so happens now that our index can be anything. So in this case, our index is going to be weight 0. So we say weight 0. This will set in the dictionary. Whenever we call weight 0, it will give us back that same weight matrix. So this will now be weights. All right, so this will be our first weight matrix. Later on, when we want to have multiple layers, we'll have to generalize this somehow. Similarly, we say for our bias that we have B0, and this is just going to be equal to bias. So now we return parameters, and we have both our our weight 0 and our b 0, right? Cool. So we can save this. All right, nice. So now we have to do our nonlinearity. For the sake of being slightly different from the homework, I'm going to use ReLU instead of sigmoid. It's the same exact thing principally. You just have to use a different forward and a different backward. So you need a different actual forward function, which is what we're going to do here, and we need a different derivative. So does anyone remember what the function for ReLU is? That's rectified linear. That's the flat one with that. Yeah.
It's 0 for x less than equal to 0 and x for greater than 0.
Yeah, exactly. One very nice way to write that is np dot max 0 in. And that's all we need. Pretty lovely. So this will just maximize across all of the dimension. If it is negative, it will become 0. Otherwise, it will just stay as it is. So this is all that ReLU does. It's one of the reasons it's so wonderful is that it basically does nothing. But it still is a nonlinearity. So now that we have both of those things, how do we do our prediction? So we have our one weight matrix, and then we have our one nonlinearity. Let's use a nonlinearity in this case, just for the sake of it. We normally don't use a nonlinearity if we have a single layer, but we can if we want to. Anyone? How do we do a single layer matrix multiplication? How do we do a single layer perceptron? We did this in homework 1. Dot product, exactly. So let's say so we have our weight matrix, which is size 17 by 3. And we have our input, which is 800 by 17. And we would like to get the correct size output. How should we do that? Yeah?
Just do W naught times dot x.
Yeah, so in that case, the dimensions are actually flipped, weirdly. So if we look at it, so if we do, ready? So print x.shape. And let's grab our weights. Let's just say that weights equals params weight 0, just for the sake of it. Okay. So I guess I'll need to do it later to show you, but let's for now let's leave it and let's see if we have any issues with it. So let's say that our prediction is going to be okay. Let's bias equals params b0. All right. So let's see. So we'll do weights dot x plus b. Cool. Anything else we need to do? There's one other thing we need to do. Activation function. So our nonlinearity, which is also called an activation function. I call it nonlinearity in this class. They're the same thing, just in case you hear the other thing. So add our bias, and then we say that our prediction is going to be equal to sigma forward, I think is what I called it, sigma forward of prediction. All right? And now we have our predict function. And later down the line, we can maybe print out shapes to see what we have. All right, so let's save that. So now let's test it. So we have, this is just going to get us the student features. This is from before, so just to remind you, this is our student who's male of race B and etc. And these are the actual scores. So what we're going to do is we're going to initialize our model, and let's see what it looks like. So we initialize our model. We have this big weight matrix, which is going to be a 17 by 3. And we have a B, which is just going to be 3 long. All right? Everything feel good there? Cool. So now let's try using our predict. So we have our model, which is going to be these, and we have our student features. All right? So let's see. Oh no, the shapes didn't work. This is, so if we go through and we actually print out the shapes, let's look at them. So print out the shape of x, so x.shape, and let's also print out, I'll put it underneath here. So this is, again, going to be one of the main things that everyone comes across on these assignments. Shapes are a little bit weird to get the hang of. Again, I recommend you really just print them out and make sure that they make sense. The operation that I showed you above, this right here, is always true. So if the shapes don't work, that's usually why, is you're doing the dot product in the wrong order. So print x.shape, and let's also print weights.shape. So dot shape is your friend, and I really recommend you use it. All right. Oh, man, I keep forgetting I can't save. All right. So now when we run it, so we already did that. Let's predict. So we have 17 and we have 17.3. Right? So this 17 means that we're only feeding in one data point at this point. This will generalize to what we want to do. So later down the line, we'll have 800 by 17, but for now, we have 17. So you can think of this as being 117 at the moment. So if we go up here, we have now that it is a 17 and a 17 by 3, or yeah, 17 by 3. So what we're doing right now is we have 17 by 3 multiplied by 17. And those dimensions don't line up. We have 3 being trying to multiply by 17. So instead what we're going to do is we're going to switch these. So I know that this is a little bit counterintuitive to what I've been saying a lot of this, but we are still doing a dot product. We are just doing it slightly differently. So now when we go here, we actually have to initialize the model. And then if we predict it, wait, sigma forward is not defined. Oh, whoops. What did I call it? Sigma forward. I didn't actually run it. That's the whole, all right. All right, cool. Man. This is the fun of live coding. It's spontaneous. At least you guys get to see me suffer through the same homework that you guys did, so that's fun. Yeah. Reduce, return to reduction. What did someone say? I'm looking for people to. So it's on the max. It's messing up. I don't know why. Here, let's debug together. Fun. This. So it's happening during the reduction. So it's trying to compare it to this 0. I'm pretty sure. I guess the NP needs an actual array of zeros, which I can do. So I can do something like this: np dot zeros len in, or in dot shape is actually better. Oh, man, sorry. Fun. So if I put it as, wait, is this? Oh, it's different. Whoops, that's why. If I do this, it should be fine. Yeah. Okay. All right, cool. So let's see if I'm right. Fun, right? All right, nice. Okay, so why don't we go ahead and just change this to ReLU? So everyone remember the equation for ReLU? Or not for ReLU, for sigmoid, sorry. 1 plus E to the negative input. All right. Oh, yeah, sorry. I'm done. By the way, I know that I'm struggling here at the moment. I promise you I've done this before. I promise I wrote the solution that works for this homework. All right, cool. Thank you. All right, so we have the predict now, and let's actually look at what we predicted. So we'll print out the actual scores and then the prediction. All right, and let's see. Not particularly great. So we were supposed to be getting 66, 69, 63, and we're getting 0.65, 0.084. And this is just because we've randomly initialized. We haven't done any learning yet. It's totally expected. All right, so that's not great. Now let's do the actual learning part. So first up, MSE. So how do we do MSE? I think people by now have probably gotten it down. So we're just going to do pred minus y squared, and then we will need to do an np.sum here. So the reason we didn't need to before was because we only had one piece of data. We don't need to at the moment because we're still feeding in one piece of data, but very soon we're going to start doing multiple pieces of data. So let's define that. That should be good. And now we actually want to find the gradient. So we have a cache, right? And it is going to, so actually I need a couple other things in cache. Whoops. So I need the x, and I also need the, yep. For MSE? We can. So if you'd like to do that, let's see the magic of this. Wow. It actually doesn't matter, weirdly. So all you're doing is you're changing the scale when you change from sum to mean. You can justify that for yourself. So it actually doesn't matter at all. But we can for the sake of making it a more justifiable thing. So now, we're looking at the gradient. So I've missed a couple of things that we need for the gradient, but let's think about what we need. So let's think out loud for what we need. So we want to go through our model, right? And then we want to be able to go backwards through it and calculate all the derivatives. In the case of ours, it's very easy for this one-dimensional thing. Let's say that we have our input, and let's also get our prediction just for the sake of doing this. In our case, we want to get every single one of these. So let's say our DW. So our DW in a single model, right? So let's actually start with going from the output. So if we're looking at the output, right? So this is going through our whole model and then the loss function, right? So we're going to have first the D loss, right? So this is going from the loss to our prediction, right? So what do we want that to be? What's the derivative from our loss that we actually calculated to our prediction? Not quite. So let's remind ourselves of what the loss is doing. So we take our prediction, and all the loss function is doing is saying that prediction minus the real label squared and summed, or meaned, if you'd prefer. So all we want to do is do the derivative of that function, of MSE, with respect to the prediction. So we've already done this in last homework. This ends up being 2 times y minus prediction. So I'll add y onto here too, just for the... So we could save it in the cache, and in the homework, I think I don't make you do that, but you can save everything in the cache if you'd prefer. And let's make it prediction minus y to be consistent. All right, prediction minus y, right? And then one little thing here is that we are actually now ending up with predictions and y's that are multidimensional. We have many predictions all at once, and we're comparing them to other actual labels all at once. We had the same thing in the MSE, right? We're looking at the differences between all of them and summing them, same as having all those data points. And now we need to do the same thing for the derivative. Luckily for us, when we're taking the derivative where there is a addition like that, we can just do the exact same operation. We can just sum them together and multiply by that scalar. So that's a nice little thing for you. If you want to justify this to yourself, you can make a little computation graph where you have 2 pieces and you compare them. But the short rule of thumb is if we are taking the derivative of a summation like this, we can just leave the summation because it's doing the same operation to every single one of them. All right. So now we have, so let's do it like this instead because this is a simple example. We have our derivative of loss, and now we want to calculate, so we have derivative from loss to our prediction, and now we want to go from our prediction to our weight. We have one other thing in the way though, right? So before we had something like this, where it was just x, if you remember, or x times d loss. Something akin to that, right? So we had that before. It'll actually be a dot product, but I'm breezing past it. But all of a sudden now we have something in the way. So what we have is an activation function. So now we need to do the derivative through the activation function back to our actual model. So does everyone remember the derivative of our sigmoid, or sigma? Exactly. And in our case, in this example, it happens to be that prediction is the output of that sigmoid, of the sigma. So in the case of this, it will be d loss times 1 minus prediction times prediction. So this is the derivative of our sigma, right? The derivative of sigma is 1 minus sigma of the thing times sigma of the thing. when you take the derivative with respect to that thing, which is an interesting property. But you can see here the first example of we have already calculated the prediction, so we just need to plug it in. All right? How well are people following along to this? Good? All right, cool. All right. So now we have a little bit of an issue, though. I've said multiply here twice, but can we actually do multiplications? For the most part, no. So we have d loss, right? So this is d loss with respect to our prediction. What should be the shape of that? All right, so this is a rule of thumb for everyone. The derivative of something with respect to something else should be the shape of that something else. That is the rule of thumb for you. Yes?
So it should be the same size as the function?
It should be the same size as our prediction. So the output of the loss function is going to be a single number because we're meaning over something. But the actual loss is going to be just it's going to be 800 by 3, which is the output of our model when we have the 800 thing, or in this case, 1 by 3. So we have something that is 800 by 3. So let's do comments. I'm going to try to do this like you guys might want to. So we have 800 by 3, right? And what's the size of our prediction? $800 by 3, actually, because we're predicting 3 different values. And then we also have 800 by 3. So we have these 3 things, right? And they all seem to be the same size, right? What do people recommend we do? So we're multiplying them together, right? And we need to get them so that they are, we want as an output also 800 by 3. Dot product? Yeah. So, yeah? So what is really funny about this situation, so I've sort of led you on all here. In this case, we are actually doing element-wise operations. So we actually can just leave them the way they are. We'll end up with the correct dimensions. This is a case where we look at it, and we can see that the dimensions do work out, and it is actually proper to do this way. We can also find that if we try to do some dot products here, if we try to mix these up, we will not actually be able to end up with the right shape. So playing this little game where you think about how this works, and the real secret here is that everything along the activation function, everything the activation function does is element-wise. So it's likewise, in its derivative, everything is element-wise. So just a little bit of a helping hand where probably a lot of people in doing the derivative of sigmoid are struggling with the dimensions. These are a little bit of helpful hints to try to get you along the way. So I'm just going to put in here so that if anyone wants to see it, we have that it's element-wise, so we can do the same thing the other direction. Now, we have one final thing. So we want to get our weights. So our weights are going to be what size? We just initialized them a minute ago. What are they going to be? 17 by 3. So we know that the derivative of weights with respect to its output is just going to be x, right? So we have something. Let's do it like this. So we have something that is going to be, let's say, 800 by 3, right? 800 by 3, or 800, right, by 17, sorry. 800 by 17, sorry, I messed it up. And then we also now have this derivative. So we know that by our calculus, we know that our answer should be the derivative of our activation. So this is derivative of loss with respect to our activation. And we're going to multiply this with our x somehow to get the right answer. Right? So we now have times dact. And dact is going to be of size 800 by 3, like we just found. So how can we do this operation such that we get the right size? We're allowed to transpose and dot product are our main operations as well as any other element-wise things. Give people a little bit to think. So transposing is swapping the order of the dimensions, and dot producting is multiplying them together where the middle dimension collapses. Exactly. So, yeah? So transpose of x, right? That's going to change it now to 17 by 800. All right? And then take dot product. Dot, dot. So exactly. So now you've seen a little bit of how we can play that game. Think about how to line the dimensions up. There are very rare cases where you can't play this game when all the dimensions are the same, but in general you'll be able to do this, and it will help you a lot in figuring out how to line up your math. I know that this is not a super intrinsically obvious way to do this operation, but I think you all agree that once we print out the actual shapes of everything, it becomes a lot more like a puzzle that you can actually solve, and there usually is a unique solution. All right, so now we have our derivative there. What will be our derivative with respect to bias? So this one's a bit of a weird one. So we know from our math that we are going to have our derivative of activation, right? And then we have the derivative of our prediction with respect to our bias, which happens to be 1, right? So we have a bit of a weird situation here. So the dimension of dact, as we've said before, is 800 by 3. But we want our bias to just have a size of 3. So how might we do that? Average it? Let's try it. So let's all remember that we're averaging this. And if something doesn't work down the line, we'll come back and think about it again, okay? I know that this is not something that I actually have an answer for you guys right now, but you'll see. Okay, times 1. Cool. So now we're averaging. The problem now is that we have to pick a dimension to average over. So if we just do mean, we'll end up with a single value output. That's not what we want. So instead, when we're doing this sort of operation, there is an input in each of these called axis. Axis will tell you which dimension to do the operation over. So the dimensions are 0, 1, etc. So in the case of this, we are averaging over this dimension because we want to end up with just this size. We want all of these to collapse on themselves. So we're going to set axis equal to 0. All right? So this should do a mean where we end up with size 3. All right? So let's remember that's what we did, and let's see if that ends up being the right idea. All right? Cool. So this is the gradient now of our very simple thing. And again, we're doing our gradient as a dictionary. So our gradient is going to be some dictionary, and we'd like to store it in some way that's going to be helpful to us. So what we're going to do is we're going to do the grad, or just grad of W0. So we're going to use the same exact notation as we did before, because this will allow us to iterate them the same way. We can just call them the same way and just say, take this with one key and this with the same key and do gradient descent on it. So we'll say that this is going to be equal to dw, and now this is going to be equal to dB, derivative with respect to bias. So now we have our grad, we have our prediction, we have everything we want, we have our loss. Now we need to put it all together. We need to update. So we have our gradients, we have our parameters, and we have our learning rate. So does everyone remember the equation for stochastic gradient descent, the algorithm that we do? Does anyone who wants to share it? So we end up with some new weights, yeah? Okay, well, just in terms of W, just for the... Exactly. And I'll change it to this notation for the sake of... Yeah. So that is our equation. That's all we need to do. And we need to do the same with bias. Exactly the same, except swap out the gradient. So first, let's see. We want our, so let's assign new params just for, I made it have a new parameters just so that you guys can like see the whole process, but you could just replace them. So now we're going to say that new params of weight 0 is going to be equal to params of weight 0, right? Because that's what we had stored already, minus learning rate times, and can we just multiply it? So this learning rate is going to be some number, and we're going to have our grad be something else, right? So that's our gradient of W. Are we allowed to just multiply it by this number? Yes, it's an element-wise operation. Just getting you the habit of, there are element-wise and there are non-element-wise, and just get in the habit of recognizing which is which. All right, this will not change the shape of this, and we know that the gradient of something should be the same shape as it, so all of these operations are totally fine. Now we do the same with bias, so we just do the exact same thing. B0 minus learning rate times grad B0. So exactly the same. Now we have our new parameters. Isn't that lovely? So let's actually call each of these. Boom, boom, boom. All right. So now we have our stochastic gradient descent. All right. So we have our very simple model here now. So we want to initialize our model. So first, we need to say that our model is going to be equal to something. So we have here that I'm going to be saying that our model is going to be equal to our initialize model. So recall what the output of that was. The output of that was a dictionary. Our dictionary is our model, right? So the settings of the parameters and the shapes of the parameters is exactly our model. It might not feel right for our model to just be the parameters, but it is the parameters and the shape of them. That is exactly our model, along with what activation functions we use. But that is exactly what we're doing. Is exactly what it is. So first, we initialize it. And in our case, we'd like to do it such that we have 17 and 3. So we know that that'll work. We're just initializing one layer right now. In the future, this won't work, but for now, it'll be fine. All right. Then what else do we need to do? So we've initialized our model. What else do we need to do? Oh, yeah, sorry. Let's just say that scale equals 0.1 for now. I'm not going to explore much about how scale works. That's in the second written bit. You can try it out and see how it works. But for now, let's just leave it at the default that I had in the homework. All right. So the first thing we want to do is we want to do our prediction. So our prediction is going to just be predict our model X. I'm pretty sure. Let's make sure that the definition's right. So predict is just the parameters and X. So that's exactly right. So that will give us our prediction, all right? And now I will point out the fact that we could just calculate the gradient right now if we want to, without ever having calculated loss. See, I was right. And to do that, all we need to do is now call our gradient function. So gradient, and it is, I think, xy, or it's cache xy. So, oh, so it should. It does it actually in the notebook, because I was going to change that in a minute. It doesn't actually yet. Here, I'll add it just for the sake of it. We're going to have to change that later on. That's I'm going from homework 1 to homework 2 and showing you how to transition the two. But yeah, so we have the cache. For right now, let's just, so I'll set cache to nothing. So cache is just going to be some empty dictionary for now. Right? We could do something with it though, but let's not for now. So now we have our SUD, right? So we have our gradient, which is going to take our cache, our X, our Y, and our model. I'm pretty sure. And our prediction. Oh, okay. Okay. We don't need our model immediately, but we should be taking it. You'll see though. Okay. So Or I guess we'll need to take it. Okay, so that should calculate our gradient. And now all we need to do is have our model be our new parameters, right? So we update using our gradient. So we're going to take our model, our gradient, and some learning rate. So our model, our grad, and some learning rate. Let's say our learning rate is going to be 001, just for the sake of picking a number. All right? Now, this is going to just look at, so this is going to do all of the input, and we're going to update it. So let's look at first what our loss is going to be here. So let's use this prediction to get our loss. So we're going to call MSE with, so let's say MSE is just going to be prediction and y of pred and y. So first up, we're going to do this. So you may notice that we're not iterating over any of the inputs. This is because we're taking in the entire data set at once. This is a big difference between the first and the second homework. We're now dealing with data that is all fed in at once. This is where that extra new dimension comes from. That's where that 800 is coming from. It's from the fact that we're taking all of the data in at once. Now, class is almost over. And it's taking a little bit longer than I thought, probably because it was a lot of discussion about the homework. Let's just finish up this little bit and let's look at if our model is able to learn. We can either continue this tomorrow, not tomorrow, on Wednesday, or we can do lecture slides covering the same material. I think this is a little bit too slow, is my read on it this class. Let's say hands up if you want to continue doing the coding on Wednesday. All right. And hands up if you want to do slides on Wednesday that cover the same material. All right, okay. Well, I recommend that you all take a look at this notebook. I'm going to at least finish off this bit. So we have loss 1 here, which is going to be that prediction from here, and then we're going to get a new prediction from our model after it updates. And then we can get a new loss. And then we can compare them. And then after this, we'll just say that our final parameters are going to be equal to our model. So our model is just going to update, and then it's going to do one update, and that's it. So we can try it out. We wanted to output the losses. So I actually did it like this. So let's say that losses equals loss 1, loss 2. Let's just say it like that. Okay. So this will just save them. If we actually do this, we end up, yeah, so, oh wait, cache is not defined. Oh, yeah, sorry. Cache. I'm not going to take the cache there. Yes, so it's outputting a, wait, I did too. Oh, I didn't redefine it. Oh my God. Okay. One second. Man, this is actually, it's pretty hard to live code, huh? I didn't realize, it's kind of stressful, actually. Okay. Last little bit, we update this. We go here, and it doesn't work. And that is because we're doing the NP mean on that. Okay. Oh, it's trying to do, okay. Well, I guess that is the lesson of, what?
You don't have a multiply symbol between 2 and
Yep, I know. It's the end of class, and so that becomes that. So I really recommend you do take a look at the notebook.